couple of things. There won't be a class on Saturday. I'm not here. We will make up for the class by shifting it one day before. So that means we'll have it tomorrow from 8:30 to 9:30. I don't think you have anything tomorrow morning, so we will shift it. I said yesterday that we'll do the tutorial before we move to matrices, but maybe we'll do matrices now and then do the combined tutorial after we do matrices. But I would strongly recommend that you there is a tutorial as well for the course. So you can go through that and the problems in the notes. I think they are the same. The solutions for the tutorial are in the notes. So I would encourage you to go through that. Okay. So the second module that we'll move on to is called is on matrices. You already saw what a matrix is, and you know what a matrix is. A matrix is essentially a rectangular arrangement of numbers, like this. Matrix has two numbers associated with it that determine its shape: number of rows and number of columns. Okay? The row numbering starts from 1, and the column number also starts from 1. So this is different from if you use programming languages like Python, where if you have a two-dimensional array, or if you have a vector or single one-dimensional array, the indexing starts from 0. In MATLAB, I think it starts from 1, if I remember correctly. But in maths, the indexing starts from 1, not 0. So that would mean this is row 3, and this is column 2. And this would be the mth column, and this will be the nth row. And depending on the number of rows and columns, we will refer to matrices. Okay, again, I repeat myself. We will use capital letters and bold font to represent matrices. So whenever you see capital letter bold font, it means it's a matrix in this course. Now, if a matrix has n rows and n columns, we say that the matrix A is a skinny or tall matrix if the number of rows is more than number of columns, that is n greater than m. Okay, then that means the matrix is like this. We say it's a square matrix when m is equal to n. We call it wide or fat if the number of columns is more than number of rows. This means, and as I've shown here, at least the convention we'll follow is we will essentially encapsulate these numbers between two square brackets. Okay. This means that the vectors that we've seen so far, you can think of them also as matrices. They're this special type of matrices which only have one column. Okay, because they only have one column, that is why we will call them column vectors. Okay, and any vector that we talk about in this course for us will always be a column vector. So, for example, whenever you see me write something like this, or like this, or in the slides or the notes, you find a lowercase alphabet that is bold. It will represent a vector, and by default, if nothing is said, and if you see a symbol like this, you should always treat it as a column vector. Okay. Because I've said column vector, that means there must be a row vector as well. Because you can, if this represents a column vector, I can have another matrix which is so before if I have a matrix with n rows and m columns, we'll say this is the n cross m matrix. Okay. That means n vector is a n cross 1 matrix. Okay. I can also have a 1 cross n matrix that looks like this. Okay. And these would be called row vector. But anytime we talk about a vector, we are only talking about column vectors. If we want to represent row vectors, we'll later on see that we use a slightly different symbol. We start with the column vector and then do some operation to it to represent a row vector. So here, this is an example of a row vector. And if you remember earlier, whenever we had a column vector, represented by, say, bold V, or underscore V. The elements were, the components of the vector were represented as small letter, not caps, a scalar. Scalars were represented like this, right, with an index. We will follow similar indexing procedure for representing the elements of a matrix. Okay, if I have a matrix A, okay, the elements of the matrix, we will use this small letter A, and it's because there are now two dimensions, right? It's not just a line like a row or a column. It's got the rows and columns. The elements will have two subscripts, I and J, and I represents the row number and J represents the column number. That means the first element of the matrix would be A11. Let's say this is a n cross m matrix. What will be the last element of the first row? A1, n or m? M. That's the column number. What about the very last element of the matrix? Bottom right. Will be ANM. And what element does Aij represent? Which row, which column? It's an element in the ith row, jth column. Okay. All right. So the individual elements of a matrix, usually of vectors as matrices, are scalars, right? It turns out that you can have matrices whose elements are also matrices. Okay? So we have a matrix like this. Okay. What is this shape of this matrix? When I say shape, I'm essentially asking you rows and columns. No, rows always come first. Is this a tall matrix or a fat matrix or a square matrix? This is a fat matrix. Okay. Now, another way that we might often or sometimes write this matrix is we might. So this is just a rectangular arrangement of 12 numbers, right? But maybe for an application that we're dealing with, maybe these numbers, right, mean something to us. The first three columns and the first two rows have some physical meaning to us. Okay? And similarly, this has some meaning. So what we might do is, instead of writing A like this, we might actually write it like this. This is A. Where B represents this, the 2 cross 3 submatrix of A. C represents the 2 cross 1 submatrix. D represents the 1 cross 3 submatrix, and E represents this 1 cross 1 matrix or the scalar. Okay. So you can write it like this, where the elements of a matrix are themselves matrices or vectors or whatever you like, or matrices in general. The only requirement is, whenever you write things like this, right? And when you write a matrix as whose components are also expressed as matrices, we say this is a block matrix representation. So here we say A is a block matrix. Okay, that simply means that we are essentially writing A as a rectangular arrangement of matrices themselves. Okay, some sub-matrices. Okay? And here B, C, D, E would be sub-matrices. The only requirement is that the columns in or the elements of any particular column of a block matrix, all those matrices, sub-matrices, will have the same number of columns. Okay? That means B and D will have the same number of columns. They can have different number of rows, but the number of columns will be the same. Similarly, for the row, any row of a block matrix, the sub-matrices of that row will have the same number of rows, but can have different number of columns. Exactly what we've seen here. here B and D have the same number of columns, 3 columns, but have 2 different number of rows. B has 2 rows, D has 1 row. Similarly, C and E have 1 column and different rows. B and C have 2 rows, whereas D and E have 1 row. Okay, you cannot have a situation like this. You cannot have one block matrix here, another one here. You cannot write it like this. It turns out this is not that useful, and so we will never. So whenever you see a block matrix, we are never talking about an arrangement like this. We are always talking about an arrangement like this. But this is a block matrix. This is a block matrix. Right. That means now if you have a, let's say we have a M. Sorry. We have an N cross M matrix. We can write the matrix like this as a block in a block matrix form. Our matrix is X. We can write this matrix X in a block format like this, with the individual elements being the columns of that matrix. Okay. Each column itself represents a submatrix. So this is in fact a block matrix representation. Because we use for column vectors and row vectors, we use small caps, bold letters. That's why I've used small x1. Even though matrices, in general matrices, we represent as bold capital letters. But because we are dealing with column vectors here, that's why I've used small x. So this essentially tells you that the matrix contains m columns, and each of these vectors will be from a particular space. In this particular example, each of those vectors xi will be from Rn, will be an n vector. Okay. That means here, this one is A1. This one is vector A2, vector A3. This is so in this process, we've actually introduced another notation. Okay. If I have a matrix X, right, we will usually write the columns as, so if I have a matrix X, the columns are represented as bold small x I. Whenever you see this, right, if you have a matrix X, then we'll represent the ith column of the matrix as bold small case letter corresponding to the matrix and the subscript I. Okay. So if I'm talking about matrix A and then I say the ith column, it would be this. If I say the fifth column, okay, now we'll look at some useful matrices that we'll often come across. Right? The zero matrix, all zeros. And so whenever you see 0 subscript n cross n, that means we're talking about a zero matrix. And this is essentially a matrix of all zeros. Right? And if you're talking about an n cross m matrix of all real entities, then these are elements of the set. If you're talking about an n cross m matrix whose elements are all complex numbers, then you're talking about or the matrix is an element of this set C n cross n. So whenever you see this, you know what it means. It's simply the set of all possible real matrices with n rows and n columns. Okay, so we have the zero matrix. A zero matrix can be of any shape. There is no restriction on if it should be tall, square, or fat. Another important matrix is the identity matrix. Identity matrices are always of square shape, and the definition is fairly simple. And identity matrices are usually represented by bold I with a subscript n. N essentially, because it's a square matrix, n essentially tells you the number of rows and columns in the matrix. So I2 would be a 2 cross 2 identity matrix. Here I've shown the example of a 3 cross 3 identity matrix. The definition of an identity matrix is this. The nth element will be 1 if m is equal to n, it will be 0 otherwise. Right? That means it's a square matrix. The elements where the row number and the column number are exactly the same are these elements. Essentially, going across the square, that means the diagonal of the square, it's as if it's the diagonal of the square. And this is often also called the main diagonal. Okay? An identity matrix is one where the diagonal elements are all one, and the off diagonal elements, elements above the diagonal and elements below the diagonal are all 0. Okay? That's essentially what this definition means. And a 3 cross 3 identity matrix is essentially this. Okay? And if you look at it carefully, right, we can write the identity matrix as a block matrix involving the E vectors. What are the E vectors that we saw earlier in the previous? What are they? Vectors where one element is 1, everything else is 0. Unit vectors, right? And for any space Rn, how many unit vectors do we have? N unit vectors. So the identity matrix is nothing but a concatenation of all the unit vectors from your Rn space and then cross an identity matrix. In fact, the columns are unit vectors. If you look at the rows, right, they also look like unit vectors except they are rotated by 90 degrees. Right, if you look at this, the first element is 1, everything else is 0. Second element is 1, everything else is 0. So that's identity matrix. Diagonal matrices, on the other hand, are similar to identity matrices, except that diagonals are just non-zero and off diagonals are all 0. Right? Something like this. And whenever people talk about a diagonal matrix, they are talking about a square matrix. Next one are what are called triangular matrices. These are again square matrices, except one set of elements is 0, everything else is non-zero. And you can have two types, upper triangular or lower triangular. If you say upper triangular, right, and this is the diagonal, all elements below the diagonal are 0. That is an upper triangular matrix. If all elements above the diagonal are 0, that's a lower triangular matrix. And that's essentially what I've written down here. And all of these have some significance. Diagonal matrix tells you has some significance. The triangular matrices have some significance. That's why we are picking them out and then defining and then providing the definition up front. And we often come across such matrices, so it's useful to know. Useful to have special names for them. Now so those are some common matrices that we'll come across. Later on, we might also talk about a trapezoidal matrix. For example, you'll often see people represent tall matrix like this, square matrix like this, and fat matrix like this. And people might draw a matrix like this, and this represents upper triangular. This represents lower triangular. And you might often see people draw something like this. This is called a trapezoidal matrix. It's really not square, but some elements are 0, especially ones below the partial diagonal of this matrix. Okay, so now we look at a useful and important operation with matrices. It's called the transpose operation. You know what this is? It's simply a process where you swap the row, you essentially convert rows into columns and columns into rows. Okay? So if you have a matrix A, and when you do the transpose operation on the matrix A, the resulting matrix is represented by A superscript P. Okay? If you started with the n cross m matrix, so you have A, and if you do the transpose operation, and if you started with the n cross m matrix, the resulting matrix will be A transpose. This will be m cross n. Essentially, the first row will become the first column of A transpose. The second row of A will become the second column of A transpose, and so on and so forth. So you start with this, and then when you do the transpose, you can think of it as either you converting the rows into columns or converting the columns into the rows. Both of them will give you the same result. Okay. This means if I take a column vector like this, this is a n cross 1 matrix. What will happen if I take the, so it will be 1, 2, 3. That means you can convert a column vector into a row vector simply by doing the transpose operation. And that brings us to how we will represent row vectors in this course. The row vectors will always be represented like this. A vector symbol transpose, because anytime you see a vector symbol, for us it's always a column vector. So if I want to explicitly tell you that I'm dealing with a row vector here, then I would put a transpose there. Okay. We will never write something like this as a row vector, at least in this course. Okay, that's just convention. This will always be a column vector, but if you see this, that means I'm dealing with a row vector. Fine. Now, if I give you a matrix represented as a rectangular arrangement of scalars, you know how to do the transpose. What if you had a block representation? How would you do the transpose? Okay, all right. So if I take A transpose here, right, what will the resulting, is it possible for me to write A transpose in terms of the submatrices, some operation on the submatrices? Okay. You can verify this. For example, you can start with this example and then verify it later on. Do the transpose of the individual elements and then see what are the corresponding blocks now. This you ready? So write down the transpose of this and then figure out what should be the block representation of A transpose in terms of B, C, D, and E. Yes, yeah. Okay, so it will be what? B transpose? Yes. So this is what you do. You take the block columns, okay, and then convert them into block rows. And then you take the transpose of individual element of each block row. That's all. Or the other way around. You take the block rows, convert them into block columns, and then take the transpose of each. Okay, and you can verify this for that 3 cross 4 matrix that we just saw. So that's the transpose operation. Now, before we move on, if you remember earlier, I said if you have a matrix A, we can write it as a concatenation of, this is n cross n, like this, as a block matrix of column vectors. Okay? We will also follow another convention of writing this as a block of rows. Okay? What does A2 represent? for A. Second what? Second column of A. Okay. So here I've written A in terms of its columns. A also has rows. That means we should be able to write A in terms of its rows as well, right? The convention we'll follow is this. We will still use small a. There will be the vector notation, but we will put a tilde symbol. Okay? Whenever you see the tilde symbol, right, that means we are dealing with the row of a matrix. Okay? But this is a vector. For us, all vectors are column vectors. They are not row vectors. That means A and A tilde cannot represent a row for us. Okay? So the ith row of A will be written like this complicated symbol. Okay? A tilde transpose I, subscript I. So the first row would be A1 tilde transpose. Second row would be A2. And how many rows do we have? All right. This is again one of the points that often confuses people. Let's do an example. What is A1 here for this matrix? Column, what is that? What about A4? Great. And if you, so that means we can simply write this as A1, A2, A3. So now, what about the first row of this matrix? And for us, the first row of this matrix will be represented as A1 tilde transpose. It's 1401. What about the second row? Minus 1, 2, 3, 4. Third row is 5, 1, minus 1, 1. What is A1 tilde? You understand the question? I'm representing the first row as the transpose of A1 tilde. So that what must be A1 tilde then? Yes, it will be a column vector 1401. Okay. So your AI tildes essentially represent the ith row of a matrix A, except in the column form. And you have to do that, and we will use the transpose operation to represent the row. That means we can write this as A1 tilde transpose. Okay. There's just one thing we need to notice. Okay. We started with the n cross n matrix. When you represent the matrix in terms of its columns, right? What you get is a block row. So here A is represented as a row, but the individual elements are columns, column vectors. Okay? Similarly, when you represent the matrix A in terms of its rows, what you get is a column vector, but the individual elements are row vectors. You see? So this is a block column. This is a block row. Okay. Next thing we look at is matrix addition. This you already know. We can only add vectors, sorry, two matrices if they're from the same space. That means you can only add vectors from two elements from n cross n. You cannot add an element from n cross n and another element from p cross q, but p is not equal to n and q is not, or q is not equal to n. This you cannot do. But if you take two elements from either this one, this set, then you can add them, and the addition operation is simple. You add the corresponding ijth elements of both matrices, and that's the resulting matrix. And because the set of matrices is a vector space, that means the resulting matrix will also be from the space Rn cross n. These are standard properties of matrix addition. Another one additional property is the transpose of the sum is the sum of the individual transposes. These are all things you can verify by yourself. We've also seen the scalar multiplication operation. If you say you're multiplying a matrix by a scalar, that means you're multiplying the individual elements from individual elements by the scalar alpha. Okay. And this we've seen before. Is n cross m a vector space? That's a yes. Set of real matrices with n rows and n columns does form a vector space. So far we've talked about essentially, if you're talking about just n vectors, we've talked about simple basic operations like scalar multiplication and vector addition. For matrices, we also saw this transpose operation. We talked about one type of multiplication operation that you can do between vectors, right? The inner product, right? You take two n vectors and there is a multiplication operation that is defined. It turns out the inner product is a generalization of a more general operation, which is the matrix multiplication operation. This again is fundamental to linear algebra. You have to understand matrix multiplications very well, because almost everything that we do involves matrix multiplication. Initially, matrix multiplication is a bit weird. The operations seem very arbitrary, and the definition that you might have seen in your maybe 12th standard maths or 11th standard maths is just one way of representing or thinking of matrix multiplication. That's often not the easiest way to digest it. It does not really reveal what is going on. Okay, so we'll spend some time talking about matrix multiplication and slowly build towards multiplying two general matrices. Okay, but there are some special rules that we need to keep in mind, right? When we talked about the inner product, we said we represented it like this. Now you're ready to say what is going on here. You are not really multiplying two column vectors. What you're doing is you're taking a column vector x, converting it into a row, and then post multiplying. That is post multiplying it by another column vector. The only condition is both x and y should be of the same size. Okay. We can multiply, or we can do a valid multiplication operation between two matrices A and B if they satisfy this condition. Let's say A is a matrix from the space Rn cross P. There's n rows, P columns. And B is a matrix from the space P cross M. Okay. We can multiply A and B like this. Or we can post multiply A by B. That means we can put B after A and perform the multiplication operation if and only if the number of columns of A equals the number of rows. If they don't match, then there is no multiplication operation possible. Okay. That's a fundamental rule. Again, this might seem arbitrary, but later on we'll see that this actually makes sense if you understand what matrix multiplications actually represent. Right? And the definition that you might be very familiar with is this definition. Right? If I gave you two matrices, like this. And I asked you to produce the product of the two matrices, you'll give me the individual elements, and you know how to do it. Take each row, and then you multiply the elements of a row with the column, and then you then produce a scalar. That's essentially this. What you might know from your 11th or 12th maths is this operation, where you know how to compute the ijth element of the product matrix C. So let's say if the product is C, using this formula. And when you multiply a n cross p matrix with a p cross m matrix, the resulting matrix will be, the common dimensions disappear. What you end up getting is n cross n. Okay. And as I said before, the inner product is essentially a special version of the matrix multiplication operation. And let's see if the conditions for matrix multiplication are actually satisfied. The condition is, if you say you're doing C equals A post multiplied by B, then this must be of size, let's say n cross p. This must be of size p cross n, and the resulting matrix will be of size n cross n. What is happening when you're doing the inner product? What are n and p when you're doing the standard inner product? What is n? What is p? No. So when you do a standard inner product, right? You're dealing with two vectors that are from Rn, right? And the standard inner product is written like this. That means you're multiplying a row vector with a column vector, or you're multiplying a matrix whose dimension is 1 cross n with a matrix whose dimension is, all I've said is one is a row vector, other is a column vector. That's 1 cross n and n cross 1. These two are the same. That means it disappears. So when you multiply this, what you get will be 1 cross 1, which is nothing but a scale. And the product takes two n vectors and produces a scale. Okay. Here, we did not just call this the product of two vectors. We called it the inner product. That means there is probably an outer product, which there is. We will see it a little later. And here, you remember the definition of the inner product? This is exactly the same as the resulting matrix is a 1 cross 1 matrix. So you will compute the element 1 cross 1 element of the resulting matrix through this formula, which is the same as how you find Cij. Okay. Now, before we can tackle and understand full matrix multiplication, A, B producing C, we will look at slightly simplified versions of A and B to try and digest what is going on. So the first thing we look at is post multiplication of a matrix by a column. Okay? It means we're talking about an operation where you have a matrix. And for now, let's assume the matrices are all n cross n. If I say I am post multiplying this matrix A by a column, what should be the shape of X? This is a matrix multiplication operation. The only thing is B is now replaced by a matrix with just one column. So what should be the shape of X? It will be cross 1, but what will be the number of rows? M, right? So when you say you're post multiplying a matrix A by a column vector, the column vector has to be a M vector. The number of rows of that column vector has to be M. Okay. And if you do this product, right, what will you get? Yes. Yeah, or n cross 1 matrix or a column, another column vector. You will get Y And the shape of Y will be n cross 1. Right? So the first thing you remember is if you have a matrix and you post multiply it by a column vector, you will get a column vector. Okay. Now let's see what the column vector is. Now, this is our original matrix. The individual elements. We are post multiplying it by the column vector X. Okay. And this we know will produce a column vector Y. Okay. So I ask you, what will be the first element of the column vector Y? So this column vector will be like this. Right? Y1, Y2, Yn. Right? I ask you, what will be the first element of the column vector given this is A, this is X? Yes, it will be A11 X1, A X2, A1 M. Right? This is how you compute it, right? Okay. Similarly, for the other elements, Y2 would be A21 X1, A22 X2, so on and so forth. That's essentially what I've written here. Okay. Now, if I do write it right, this will be A21 X1, A22 X2, A2M XM, or Y and Yn will be AN1 X1, AN2 X2, ANM X2. Right? Okay. If you look at these equations, right? If you look across the equations, right? This is all X1. If you look at all the terms in front of X1, right? You get a bunch of AIJs. Similarly, if you look at all the elements in front of X2, you get a bunch of AIJs again. What do these AIJs in front of X1 represent? Essentially A11, A21, A31, so on and so forth to AN1. Those numbers. Well, those are essentially the first column of A, right? What about this second column? That means another way for me to write these bunch of n equations is like this. I say you take the first column of A, A11, A21, AN1, multiplied by the scalar X1, and then add. You take the second column, sorry, A12, A22, AN2, multiplied by X2. You take the last column, this A1M, A2M, ANM, XM. Right? And what will I produce? I'll produce a Y column vector. All I've done is write this same set of n equations or linear equations using column vectors. That's it. I've not done anything else. Because if you multiply, if you scale each of those columns and add all of them together, Y1 will be equal to this, Y2 will be equal to this. It's just another way I've written it. But that means when you say you post multiply a matrix A by a column vector X, what you're doing is you're taking the first column of A, you are scaling it by some number X1. You're taking the second column of A, you're scaling it by some number X2, and so on and so forth. You're taking the last column and you're scaling it by some number Xn and adding them all together. Essentially, you are taking a linear combination of the columns of A. And that's very important. once you have to get this because a lot of what you'll talk about later on depends on your understanding of matrix multiplication like this. Whenever you post multiply a matrix by a column vector, one way to interpret that operation is you are taking a linear combination of the columns of A, and how much of each column you're taking is given by the column vector X. For example, I'm taking, so one way to interpret AX is I'm taking X1 amount of the first column, I'm taking X2 amount of the second column, and XM amount of the mth column, and I'm adding them all together. So you're essentially mixing the columns of A to produce another column. Right? That is why the resulting column has the same shape as the column, the shape of the size of the columns of A. Okay, Y is from Rn. The columns of A are from Rn. Okay. So post multiplication by a column vector is a mixture of columns, okay? And the exact mixture is given by the column vector X. How much of each column you take. Okay. We can similarly extend this idea to row vectors, right? But now you can't do a post multiplication. For example, if I have A, which is n cross m, I can't multiply it by a row vector. What is the shape of this vector? Well, it'll be 1 cross something. I can't do this because n and m don't match. So this is not post multiplication by a row is not possible. But I can do this. But what should be the shape of X transpose? It'll be 1 cross something. No, A is n cross n. Well, the number of rows of the first matrix must match the number of columns of the first matrix must match the number of rows of the second matrix. If the number of rows in the second matrix is n, the number of columns in the first matrix must be n. So this must be a 1 cross n row vector. Okay. And what will you get if you do this operation? So you'll get y. We will also write it as transpose because we get a row vector. And the shape of that will be 1 cross. Okay. So earlier we saw if you post multiply a matrix by an appropriate column, you get a column. If you pre-multiply a matrix by a row, you get another row. Okay. And you can't do the other way around. You can't pre-multiply by a column and post-multiply by a row. In the previous case, we saw that whenever you post-multiply by a column vector, the operation you're doing is you're taking the linear combination of the columns of A to produce another column. What do you think is happening here? When you pre-multiply a matrix by a row vector. Yeah, exactly. Now we are taking the pre-multiplication by a row vector is a process of taking the linear combination of the rows of A to produce another row. So that's essentially what I've written here. This is equal to, in fact, I should not be writing it as Y. I should be writing it as Y transpose by a convention. That's wrong. Right? The new row vector that I produce is a linear combination of the rows of A. See the A tilde, AI tilde, that means that's the ith row of A. You take xi amount of the ith row of A and you add them all together to produce a new row vector. And this is the ith row. You can arrive at this through the same procedure. So I will leave that as an exercise for you to do. So you have A. So this will be x1, x2, xm. And then you have the A matrix, A11, AN1, A1m, ANm. If you apply the definition of matrix multiplication, you will essentially now have m set of equations where y1 will be equal to something, y2 will be equal to something, and then you should be able to then arrive at this expression. Just like how we arrived at the expression for post multiplication of a matrix by a column. So again, when we're doing pre-multiplication by a row, you're taking the linear combination of the rows of A, and the exact mixture of that linear combination is given by your X transpose. With those two definitions, those two are very important that you're comfortable with that. Then we come to the general definition of the multiplication of two arbitrary size matrices. A is n cross p, B is p cross n, which will then produce a n cross n matrix. Okay. Turns out there are four ways to view this, or four interpretations of matrix multiplication. Okay. The first is called the inner product interpretation. Second is the column interpretation. Third is the row. Fourth one is the outer product interpretation. We look at the inner product first. The inner product interpretation is what we know from our high school maths. Okay. In the inner product interpretation, or at least the inner product view of matrix multiplication will allow you to compute individual elements of the matrix C. Okay. That means if you view matrix multiplication as an inner product operation, you can compute the ijth element of the matrix C, Cij, okay, as simply the inner product of the ith row of A and the jth column of B. That is all you have to remember. And in fact, this definition we know how to compute, right? That is nothing but you're taking the ith row of A, jth column of B, and you're taking their inner product. And inner products produce a scalar, and the exact scalar they will produce is Cij. That means the first one element of the matrix C will be the inner product of the first row of A with the first column of B. The second element in the first row will be A1 building B2. And in fact, if you remember how you do the matrix multiplication operation, you'll see that this is exactly what you're doing. You'll go across the row, go across a particular row in your first matrix, and then go across the elements of a particular column in your second matrix and multiply the individual elements and add them together. That's nothing but an inner product operation. Okay. So in the inner product operation, the individual elements of or inner product interpretation, the individual elements of the C matrix is simply the inner product of a row from A and a column from B. That's the standard view. We look at the column view. Okay. In the column view, we have the matrix A, B, right? We keep A as it is, okay? But we represent B as a block row, or we represent B in terms of its columns. Okay, that's what I've written here. I keep A as it is, and I express B in terms of its columns. Okay. And the resulting matrix C is nothing but each of the individual columns of B be multiplied by the matrix A. So if you write it like this, then the resulting matrix will simply be A times B1, A times B2, A times Bm. Okay. That means the first column of C will be A times B1. The second column of B will be second column of C will be A times B2, and the ith column of C will simply be A times. Yeah. Okay. That means the ith column of C is obtained by post multiplying A by the ith column of B. Okay. And what are we doing when we post multiply a matrix by a column vector? when we post multiply by a matrix by a column vector, we are taking the linear combination of the columns of A, and the mixture for the linear combination is given by the column vector. That means one interpretation of matrix multiplication is when you do X, C equals AB, the ith column of C is essentially a linear combination of the columns of A, and the mixture for that linear combination comes from the ith column of B. That's exactly what I've stated here. Okay. Matrix multiplication, the resulting columns are a linear combination of the columns of the first matrix, A matrix. Okay. So C, the columns of C are related to the columns of A because the columns of C are linear combinations of columns of A. Okay. And that's exactly what I've written here. The jth column of C is given as a linear combination of the columns of A with the mixture coming from the jth column of B. If that is the case, then you're probably already you already know what I'm going to say next. In the row interpretation, we have AB, we leave B as it is, but we represent A in terms of its rows. I think that means we're representing A as, so what I've written. We leave B as a matrix and we represent A as its rows, and the resulting matrix will simply be the individual rows of A pre-multiplying the matrix B. Okay? That means the first row of C will be the first row of A pre-multiplying B. The second row is second row of A pre-multiplying B, and so on and so forth. And what are we doing when we do a pre-multiplication operation like this? By a row, we are taking the linear combination of the rows of the matrix A, and the mixture for the linear combination is coming from the row vector X. That means when you do matrix multiplication, the rows of the resulting matrix are linear combinations of the rows of the second matrix, B matrix. Okay? And the exact mixture of the linear combination is given by the individual rows of A. Okay? The ith row of C is a linear combination of the rows of B, and the exact mixture is given by the ith row of A. Right. Now, if you see the column interpretation and the row interpretation, right? We left one of the matrices as it is, and we represented the other matrix as a block column or a block row. So here, in the column view, we left A as it is, and we represented B as a block row with the individual elements being column vectors. In the row interpretation, we left B as it is, and we represented A as a block column with each element of the block column being rows of A. It turns out you can do something similar. In fact, you're doing something similar in the inner product interpretation as well. But before we look at that, we now have to define this outer product operation. Right? When we said we are doing an inner product, right? We said, well, if X and Y are from Rn, we can think of these as n cross 1 matrices. That means I can do a valid matrix multiplication operation like this, where this is 1 cross n, this is n cross 1, and the resulting matrix is a 1 cross 1 matrix or a scalar. Okay, that's an inner product. Can you do this? Is this allowed? Well, I am essentially asking, do the shapes of X and Y transfers, are they compatible for matrix multiplication? What is the shape of X? Column vector. N cross 1. What is the shape of Y transpose? Yeah. 1 cross N. Both are from Rn. Can you multiply these two together? You can, right? This is the same. But what do you get when you do this? Sorry? Are you sure? Yes. That's essentially the outer product operation. Okay. If you do XY transpose, you essentially now produce a n cross n matrix. Okay. But we can generalize this. Okay. What if X is from Rn, Y is from Rm? Can I do this? Am I allowed to do this? No. Why? What is the shape of X transpose? No, row vector. N, because X is from Rn. What about this? Not compatible. But can I do this? What is the shape of X now? Yes, you can multiply. But the only thing is what will result is the outer product, the two vectors don't have to be from the same space. For inner product, they have to be from the same space. Okay, all right. So inner product, it's a row multiplied by a column like this. And this produces a scalar. Outer product, it's a column post multiplied by a row. Okay. Now with that in mind, we can make sense of the inner product operation by essentially decomposing A and B as a block column and a block row. Okay. Now, if I write A as a block column, let's see. If I write B as a block row, that means what I will then produce is it's like this, right? I can represent A as a block column if I write A in terms of its rows. Okay, that means I write A like this. A1, A N. I can represent B as a block row if I can write it as write it in terms of its columns. Okay. And I've not done anything. I've simply written A and B in terms of their rows and columns. That's all. I've not done any other operation here. But look at this. What does this look like? It's as if you're multiplying a column. Agreed, it's a block column. But assume you don't know what is inside, right? All you can see a column multiplied by a row. That means that is an outer product. Okay. Before that, my discussion of outer products was not complete. I did not. I mean, I told you how to do. I did not say what the individual elements will be. Okay. You know how to do the inner product. You multiply the individual elements, add them all together. What will happen if you do this operation? A column post multiplied by a row. What will be the elements of the resulting matrix? Well, the first element will be x1, y1. That's it. There is only one column and one row. Product of those two. Second column will be x1, y2. Sorry, not second column. The first row, second element will be x1, y2, so on and so forth. Right? If you look at the resulting matrix, right? In the resulting matrix, you can see that you can think of it two ways. The resulting matrix is has essentially columns which are the columns of the resulting matrix has columns essentially where the columns of the resulting matrix are columns of X scaled by a certain amount. So here, this is the column of X multiplied by Y1. This is the column of X multiplied by Y2 and so on and so forth. Another way to see it is the rows of the resulting matrix are scaled versions of the rows of Y. Right? And the scaling is given by, for the rows is given by your X's. Okay. Now, from the definition of the outer product operation, how do you find out the ijth element of C from this representation? What will be the first element of, or what will be C11? Well, it will be the first element of A multiplied by the first element of B. That will be A1 tilde transpose B1. What will be the second element? Well, it will be the first element of A multiplied by the second element of B. It will be A1 tilde transpose B2, so on and so forth. And what will be the ijth element? AI. Exactly this. Okay. But here is the beautiful part, right? The matrix multiplication operation, on the outside, it looks like you're multiplying a column by a row. That's an outer product. But the individual elements of the resulting matrices are all inner products. Okay. Is that clear? If that is clear, the last interpretation, outer product, is essentially in a way, complement to this. Inner product, you are doing column multiplied by a row. In the column view, you have a matrix post multiplied by a column. In the row view, you have a matrix pre-multiplied by a row. You should already be able to guess what the last view is going to be. It's essentially a row multiplied by column. Okay? That means here I chose to represent A as a block column and B as a block row. You could ask, well, what if you do the other way around? What if I represent A as a block row and B as a block column? That's essentially the last view. Okay. Let's go look at it. Okay. We have C equals AB. We represent A as a block row and B as a block column. On the outset, it's essentially a row multiplied by a column, which is an inner product operation. And how do you compute the inner product of two vectors like this? If you have x1 to xn, or here xp, and if you have y1 to yp. Well, it's simply x1 y1 plus x2 y2 plus so on and so forth to xp yp. You can do the same. You have p columns here, p rows here. That means I should be able to do that operation. That means my resulting inner product will simply be A1 multiplied by B1 tilde transpose plus A2 multiplied by B2 tilde transpose, so on and so forth. And what are these? So these are essentially A1 B1 tilde transpose plus A2 A B B B. What are these though? These individual elements. The individual elements are outer products. A column multiplied by a row. First column of A multiplied by the first row of B. The second element, you have the second column of A multiplied by the second row of B. Okay. And each of these is an outer product. And what is this? And what do outer products produce? They produce matrices. Right? Okay. In fact, okay, what is the shape of the first column of A? is, remember here, n cross p and b is p cross n. What is the shape of A? Shape of A is n cross 1. The first column of A is n cross 1. What about the first row of B? It's 1 cross n. So if you multiply these two together, what do you get? That means each of these terms, right, produces an n cross n matrix, and you're essentially adding them all together to produce C, which is an n cross n matrix. Okay. In the outer product view, the overall operation is an inner product, but the individual elements of those inner product, the multiplications that you do in the inner product, are outer products. Okay. And that's essentially the 4 views. Right? And we'll see where each of these become useful. From a geometrical perspective, we'll see that the column view or the row view or the outer product view is quite useful. And we'll see where these things come up as we go through the material. Okay. Can we look at some properties of matrix multiplication now? Okay. An important property is that matrix multiplication is not commutative. AB is in general not equal to BA. In fact, you might not even be able to do BA. If you might be able to do AB or BA or not both or neither of. It's not commutative. It's distributive, associative, and the transpose of a product of two matrices is essentially the product of the transposes, but in the reverse order. These are all again things that you can verify from the basic definition of matrix multiplication. And if you scalar multiply a product, it's equivalent to scalar multiplying one of the matrices before you do the product. Again, these are relatively trivial properties, but the most important one is this, and this is also useful to remember. See, the first time you come across the 4 views, it can be very confusing. So what I would suggest you do is when you go back today, or maybe tomorrow, you make up 2 matrices yourself, whatever matrix you want, okay? And try and compute the resulting product matrix C using the 4 ways of computing C. Inner product, where you compute the individual elements as the inner products of a row of A and column of B. In the column view, you compute the columns of C as a linear combination of columns of A. In the row view, you compute the rows of C as a linear combination of rows of B. In the outer product, you compute the individual P outer products of your matrix of the first column, ith column of A multiplied by the ith row of B. Ith column of A multiplied by ith row of B, and adding them all together. Right? And once you do this, maybe then things become a little clear. Okay, we discussed about linear functions in the previous class. Right? What do you remember the definition of linear function? Maybe that one sheet, the sheet now, maybe we should give the you have place give it to. That's simply the definitions, so that you can quickly refer to it if you don't remember the definition. What is the definition of a function? Well, this is in general a function that maps elements from Rn to a real number, and it must satisfy the superposition principle. Right? A linear transformation is simply a generalization of that definition. In fact, linear functions we'll see are a special case of a linear transformation or linear map. Right? Linear map or linear transformation essentially takes elements from Rn and produces an element. It does not just produce a real number, it produces an element in Rn. Okay. When n is 1, we call it a linear function. That's all. Okay. And this function or this map or this transformation F satisfies the superposition principle. That's all. If you have a transformation or a map that takes elements from Rn, earlier when we saw about linear functions, right? It was taking elements from Rn and mapping them to the real line. Now what we have, it's not that. It takes elements from Rm. It takes a point from here and maps it to a point here. Okay, that's it. And if this map satisfies the superposition principle, then we say that it's a linear transformation or a linear map. Okay. So that means, for example, if I take an element from here, that will be a column vector X. And if I apply f of X, what I will get will be another column vector, except X was from Rm. The resulting column vector will be from Rn. Okay. And each element would then be some function like this. Okay. So you take the values of X, do some operation, and then produce the first element of f of X. You take the elements of X, do another set of operation, compute the second element of f of X, and so on and so forth. That's essentially what I've written here. It turns out that this map f of X will be a linear map or a linear transformation if the individual functions here, right, are all linear functions. That means f1 of X takes an element from Rm, produces a real number, and it satisfies the superposition principle. f2 of X takes an element from Rm, produces a real number, and it satisfies the linear superposition. Functions f1 to fn are maps from Rm to R and produce and satisfy the superposition principle. Then the entire linear transformation is a linear transformation. Okay. That means we saw earlier that if you have a function, let's say g, right, that or f or g that takes elements from Rm and produces a real number, and if g is linear, if it's a linear function, right, that means we said g of X can be written or expressed as an inner product operation, right, like this. A linear function can always be represented like this by appropriate. We can always find a W such that g of X can be written as Wx or W transpose X. Okay? And W is a constant. Okay, and W depends only on G. X you are free to choose. You can put any number into the function, but W is determined by G completely, or G determines W, but W determines G. Okay? That means if I have a linear transformation, right? That would mean that that each of these individual functions is a linear function. If each of them is a linear function, I can represent each of those functions like this, right? A row multiplied by my vector X. That's exactly what I've written here. If f1 is a linear function, that means I can write it like this. Some constant row multiplied by X. If f2 is a linear function, then I can write it as some constant row multiplied by so on and so forth. Okay. That means for the n linear functions you have n rows. Okay. And because X is from Rm, what would be the shape of AI? In this case, I've written as AI tilde. What is the shape of this? X has a shape n cross 1, m cross 1. This will be. Okay. That means now you have a set of rows, right? Each of them has m columns. That means you can take X out and write it like this. That means if you have a linear transformation, you can always express any linear transformation as a matrix post multiplied by a vector. It's exactly it's a generalization of this idea. A linear function can always be written as W transpose X. A linear transformation can always be written as a matrix post multiplied by a vector. That means these matrices that we talk about are interesting. Each one of them can be thought of as representing a linear transformation. You can use that matrix to transform a vector X into another vector, and that transformation will represent a linear transformation. Okay. So matrices represent linear transformations, right? That means if you have a matrix that is n cross m, this matrix A can be used to take elements from Rn to produce elements in Rn. If this is X, you can produce an element in Rn by doing A into X. And this Ax will represent some linear transformation. So when you see matrices can be data. Like if you have an image, you can represent as a matrix. Another way to view a rectangular arrangement of numbers is that it represents some linear transformation. And if A represents a linear transformation, okay, the rows and columns now have an interpretation. Okay. If you have an n cross n matrix, the matrix takes elements from Rm, produces elements in Rn. That means M is the dimension of the domain of the input space of the linear transformation. N is the dimension of the output space. Okay. So if you have the matrix A, it will only take elements from Rm, if this is an n cross n matrix, and it will produce Rn. If you have X, it will produce X. That's one way of thinking about the matrix. The number of columns represent what can go in as a post multiplication. The number of rows represent what comes out after you do the post multiplication by a vector. Okay. Now that brings us to stage where now we can try and make sense of why matrix multiplication has this weird definition, and why it has these strange rules saying the number of rows of the first matrix, number of columns of the first matrix have to match the number of rows and all that. Okay. Let's say we are considering two linear transformations, F and G. And for simplicity, let's say these are linear transformations that take elements from R2 and produce elements in R2. But there is no reason why you should restrict yourself to just 2 and 2. It could be mn, doesn't matter. I am using 2 and 2 just for the sake of demonstrating things a little easier. Makes the demonstration becomes a little easier. Okay. If F and G are linear, right? That means if I take a vector X, right, and compute f of X, the first element of the resulting vector of f of X will be of this form. The second element will be of this form. Right? Because each of the elements of your f of X will itself be a linear function. And any linear function from R2 to R can be written like this. Right? Or another way to think about this, if X is X1, X2, this can AX1 plus BX2 can be written as the inner product of A and B with This is exactly what I've written here. Each element is an inner product of a vector with X. And the second element is simply the inner product of C and D. Similarly, G, let's say we have another linear transformation G, which with an input U. U is also from R2, so it's U1, U2. The first element of V is given by alpha U1 plus alpha B2. This is essentially inner product of alpha beta with U. And the second element is simply the inner product of gamma and delta. Right? Now, if you simply concatenate these rows, right, you can now represent this linear transformation F as a matrix multiplied by X, and the matrix will simply be A, which will essentially be the rows AB and CD. Similarly, for V, it's a 2 cross 2 matrix whose rows are alpha, beta, and gamma, delta. That means Y can be represented as A times X, and B can be represented as, or G can be represented as B times U. Or F represents, A represents F, and B represents G. Okay. Okay. Now I ask you this. Let's say I have a vector from R2, X. I take X and then I apply the first linear transformation F. This produces a vector from R2, right? Because F and G take elements from R2 and produce elements from R2. That means I can ask, well, what if I take this element from R2 and then I apply G on that? You're essentially doing two operations, one after the other. I take something, I transform, and then I produce an output. That output is then transformed into something else. I do F first and then I do G. Now, given the definition of, this is the original definition of F and G. I can ask you what will be the resulting vector. You can simply compute it from here. So if I take X, right, what I will get will be AX1 plus BX2, and the next element will be CX1 plus CX2. If I input this to G, U1 will simply be this, U2 will simply be this. So you simply substitute this for U1 and this for U2 here. And if you multiply it out, right, that'll essentially give you the two elements of G of F of X. Okay? And if you do the multiplication, right, what you will get is essentially this. Actually, yeah, I've done a mistake here. This should be, this is okay. These should be X1, X2. So what should come here is, it looks like I've swapped my discussion. I said do F first and G later. Here in the slide I've done G first and F later. That's why I started with U as the input. Okay? I hope that is not confusion. If you do the same thing, right, what you will end up getting finally is this. Will look like this. And this can be expressed as some matrix given by this multiplied by U. So F of X was represented as A times X. G of U was represented as B times U. Now F of G of U can be thought of as, well, F of B times U, right? Because G of U is BU. F of some vector is A times that vector. That means this is A times B times U. And that matrix AB is essentially given by this. Okay? That means when you do matrix multiplication operation, all you're doing is you're doing a composition operation of linear transformation. That means you're saying, I first do the B operation, I take the result, and then I do the A operation. So if I have A matrices like this, multiplied by X, all you're saying is, I first do the transformation represented by AK, I take the result, I then do the transformation represented by AK minus 1, so on and so forth. So one way to look at matrix multiplication is you're essentially dealing with composition of linear transformations, or you're essentially doing one linear transformation after the other to the input that we have. Okay? That means whenever you have a matrix, we can think of whatever goes on the right-hand side of the matrix as the input, and what comes out through AX on this side of the matrix. And the reason the rows of A have to match, or the columns of A have to match the rows of B, is if AB represents a sequential operation that you're doing, then the output of my previous operation has to be compatible with the input of the current operation. If the output from the previous operation is not compatible with the input of my current operation, I cannot operate on. Right? The output of B, let's say this is P cross N, this is N cross P. B produces an output from the P, RP. Right? For you to post multiply A by B, A has to take inputs from RP. If it does not take inputs from RP, then A cannot operate on the output that comes from P. That's essentially the reason why you have the condition. So whenever you do matrix multiplication like this, right, the interface between the two matrices, right, have to be compatible. That's essentially the condition, that number of columns of A have to match the number of rows of A. If they are not compatible, you cannot multiply. Okay, all right. We will stop here. We are almost done with the matrix module. So maybe we will finish this tomorrow and do the tutorial for the rest of the first module and this module tomorrow. So we'll have the class at 8:30 to 9:30 tomorrow, because I'm not here on Thursday. Thank you. Yeah, but please go review this. It requires maybe a little bit of time for you to become comfortable with this, but it's not complicated. This needs time. Okay.